Okay, this is a quick video about reference frames in 1 and 2D. This is about Galilean reference frames, so regular, not special relativity. And when I say 2D, honestly, if you understand 2D, you can do this in ND. Okay, so let's get started. Let's start with 1D. Let's say that I want to know the position of some object. Okay, it's a green ball. Right now, the green ball is just sort of floating there, and I need a way to tell people where to look for it. So I go, oh, okay, fine, x equals 3 meters. The problem is, this doesn't really make any sense. 3 meters from what? And so what I do is I set up an origin and I say, okay, well, look 3 meters from my origin. And this is a pretty good labeling system. The problem is that I might have more than just a green ball I want to keep track of. And so I really ought to pop a label on the green ball. So I'll call it XG. And now this is pretty great. Now here's the problem. The problem is some other person puts their origin in a different place. This person puts their origin here, and they are going to have a completely different label for this object than the other person does. Galileo was probably not the first person to think about this stuff, but he was the first person that we know of to formalize it, and so that's why we call this Galilean relativity. Really, the person in this frame says xg equals 1 meter, and really that means that this label, xg, it can't be two different things. This label is insufficient. So really what we ought to be doing is we ought to call the orange frame frame A and the blue frame frame B, and a much better labeling system would be something like this. The position of object G in frame A is 3, and the position of object G in frame B is 1. Now this is a complete labeling system. Now, first I say which frame to look in, and then I say where to look. Okay? Now, in addition to seeing the green ball, guess what? These frames can see each other. This is the position of the blue person in the orange person's frame, and this is the position of the orange person in the blue person's frame. And just like they give the green ball coordinates, they can give each other coordinates as well. The position of B in A's frame is 2, and the position of A in B's frame is -2. Notice how those two are negatives of each other. That will always be true. If you ever look at flipped indices, you'll always have a minus sign. Another way to say that is, if you are to the left of me, then I am to the right of you, assuming we're both facing the same direction, of course. Okay, so we are going to formalize all of this and say, how do we get from one frame to another? The way you find out what the coordinates of object G in frame A are look at what the coordinates of object G in frame B are. That's that, 1 meter. And then add the distance between the two coordinates. So that is this distance. In other words, the total distance in frame A is this distance, and it's made up of the position in frame B plus the distance between frame A and frame B. So visually, that's pretty clear. One other thing to think about is, what happens if one of the frames is moving? In other words, it has some velocity. So notice I just moved the orange frame 1 unit to the right. And when I move that unit 1 unit to the right, really it brings its origin with it. So I actually have to relabel everything. And so now my origin has shifted, my position of B with respect to A has shifted, and also the way that A labels the position of the green ball has shifted as well. If I want to talk about how the change in position occurs across frames, actually the rule is exactly the same. The change in position of G relative to A, remember on this side, this was 1. Everything changed by actually -1. Everything decreased by -1. The position of the green ball, according to frame B, that's 0. Frame B didn't move as far as frame B is concerned. The green ball is still where it was before. And we have the change of frame B relative to frame A. So frame A moved forward 1. And so according to frame A, this is the position of frame B according to frame A. That must mean that frame B moved backward 1. Another way to say that is the velocity of frame B relative to A is equal to minus the velocity of frame A relative to frame B, just like for our position rules. A nice thing here is that if the changes in position obey the same rule, then so do the velocities. Because honestly, velocity is just change in position over time. Now, if you know calc, you may have just guessed this immediately. You may have just said, take the derivative of everything, dx dt, ga equals dx dt, gb plus dx dt, BA. But of course, you don't need calculus for this when you can just do a little picture and then you can just read it off the picture as we've done. Anyway, if the rule for velocities is that, then the rule for accelerations is exactly the same. And we don't really need much else to talk about. This is basically it. In one dimension, we have just invented all of the rules we need to convert from one reference frame to another reference frame. So what do you do with all this? I'm going to give you an example. Okay, so here are our rules, and here is our first example problem. We'll do another example problem in 2D later. So this is a person, call it person A, and they have some speed, and they want to throw a water bottle, which is yet another object, to their friend who is 5 meters in front of them and running at 15 meters per second. And here's the catch, they're accelerating. So they want to throw it straight ahead. And we're going to ignore gravity because honestly, we're really in one dimension anyway. We want to know what's the minimum speed they should throw it with relative to themselves so that their friend can catch it. Now pause and just take a minute here, because understand that there's one person in back and another person in front. The person in front is moving faster, and to make life complicated, they are accelerating. So however fast this person throws this ball, it's going to have to be fast enough to not only catch up to the speed this person has and surmount the distance between these two, but it's also going to have to account for the fact that this person is speeding up and will get farther away as time goes by. So we expect the number to be pretty big. And so let's see how we're going to solve this. I'll say this is a lot of words. This is a pretty difficult problem, but if you think less and simply try to apply these rules, it gives you a kind of framework for solving problems like this, which makes it require less cleverness. Anyway, let's get to work. Let's see what they give in this problem. In this problem, they give us the velocity of object A with respect to the Earth. That's person A. They're running at 10 meters per second. The problem also gives us the position of person B relative to person A. They say that person B is 5 meters in front of them. That's the position of person B relative to person A. They also give us the velocity of person B relative to the Earth. That's our 15 meters per second. And they give us the acceleration of person B relative to the Earth. And this is what the problem wants to know. What's the velocity of the water bottle relative to person A? So you see the issue here. One of the reasons this problem is so hard to read is because there's so many reference frames. So what we want to do is pick one reference frame and stick with it. And a clue about which reference frame to have is this is actually a problem about collisions. They want to throw it so their friend can catch it. And I'm going to tell you that that's a collision. And for a collision, this is the big idea. The final position of the water bottle has to equal the final position of person B, and that is in every single frame. That is not something that's frame dependent. Either they're in the same position or they aren't. And another way to say that, these are incomplete labels. They don't have reference frames. Another way to say that is that the position of the water bottle in the frame of person B has to be 0. In other words, the water bottle is at person B's origin, and that's why they're in the same place. So that's the frame we're going to do this in, because whenever you have a 0, it's nice. So let's use our 3 transformation equations. We're going to find the water bottle in frame B, the water bottle in frame B, the water bottle in frame B. Okay, so let's start with the first one. We need the position of the water bottle relative to person A. That's not a problem at all because the water bottle is in person A's hand. They start at 0. And we need the position of person A relative to person B. That we are more or less given in the problem, so we know we're going to have a minus sign in there somewhere. And so this is 0 minus 5. Okay, easy peasy. Next, we move on to the velocity of the water bottle with respect to B. That's the velocity of the water bottle with respect to A, and this is an unknown. That's all kind of the whole point of the problem. The problem here is I actually don't know the velocity of A with respect to B, but I can use my same velocity decomposition rule. In other words, the velocity of person A with respect to person B, velocity AB equals velocity of person A with respect to E plus the velocity of E with respect to B. The rule here is this. If you want A with respect to B, you write 2 velocities on the right-hand side. The first one, the very first subscript you write, is the first subscript on the left. So that's A. I want the object A. The last subscript you write, that's a B, that is this one right here. So that's B. In between you sandwich the exact same letter. It could be any frame you want. In this case, I put E because I happen to know information about both objects in the E frame. So the real rule is, all these rules are really just index manipulation. You look at what indices you want and you rig it so that you end up with those indices at the end. Between those two indices, you sandwich whatever you want so long as it's the same letter. Okay, anywho, I've used this same trick again. This is something I know, and this is something I know. I actually know the negative of this. Note that it's EB and not BE, and so you'll see a minus sign appear. This is a minus 15 because what I'm given is VBE equals plus 15. Okay, and then the last thing to solve for is the acceleration. I need the acceleration of the water bottle relative to person A. That's 0 after it leaves their hand. I know you might be thinking, wait a minute, don't they have to accelerate the water bottle? They do, but our problem begins after that has occurred. And now we need the acceleration of person A relative to person B. And so that, again, is something that we can work out. The acceleration of person A with respect to person B is AE, EB. Ooh, that's a capital A. I don't know why that's a capital, but it's meant to be a lowercase. Anywho, the water bottle doesn't accelerate. This person doesn't accelerate, and we have the acceleration of B relative to E, so you're going to see another minus sign occur in just a second. Okay, so I admit this is a lot, and if it's your first time seeing it, it may seem rather confusing, but what I'll say is that these rules are always the same rules. You don't need to be clever about how you apply them each time. Okay, so now that we have that, now that we're done with the relative velocity part, we just go to our regular, plain old boring one-dimensional kinematics. And what we say is we want it so that the final position is 0. That's how we know they'll crash into each other. So the final position is 0, and these are things that I've worked out up here. And so this is a quadratic equation, which we can solve for t. It might alarm you at this point that we have one equation and two unknowns, but don't let that bother you. You solve as far as you can, and then you deal with it. So if I use quadratic equation on this, I end up with something that looks like this. And here's a thing to consider. You got a square root in here. If that square root is negative, then you're not going to get a real solution. And this problem is asking, what is the minimum speed they should have? And you can agree that if v is a very large number, that square root will be positive. There's no problem. There are solutions for the water bottle hitting the person. If v is small, you might end up with an imaginary number, and that's bad news. And so what we say is, let's make sure that that square root stays positive. And if we do that, we say, all right, v has to be at least 15 meters per second. If it's less than that, then we end up in imaginary land, and then we don't have any solution. The other way to see this, again, if you like calculus, is you might see what is the minimum speed they should throw it at. And I think it's interesting just to see that you can get the exact same result. If you solve this top line for v, you end up with something that looks like this. And note that if you take dv dt and you set it equal to 0, which is how you're supposed to find minimums, you'll end up with t equals 1. And if you bring back t equals 1 and you plug it up back there, guess what? You get the exact same number, 15 meters per second. Okay. Awesome. That's about all there is to say in 1D. Let's take a look at what this looks like in 2D. Okay, so here we go. We're in 2D. Here is my green ball again. So notice I don't have a coordinate system, so let's set one up. In this case, I have a 2D coordinate system. And if I want to put a label on it, I need two numbers. I need an x coordinate, and I need a y coordinate. So that's what those two numbers there are, okay? And now, just like before, we'll say, wait a minute, what if somebody puts their origin somewhere else? So now I have two reference frames, person A and person B. Person B has his coordinates and person A has her coordinates. And they can also see each other, just like they could in the previous frame. So according to person B, person A is over here in negative town somewhere, right? And according to person A, person B is, I don't know, in the first quadrant, whatever you want to call that. Okay. So we can also talk about, just like we did last time, we can talk about the distance between the two observers, between these two frames. And then, honestly, guys, that's really it. You just go back to the same rules you had before, only now you have two equations instead of one equation. Okay. The reason I can say that is because the beauty of coordinate systems is I can look at independently each coordinate system at the same time. Okay. And so here's the thing. Instead of writing two equations, we're going to adopt vector notation, and we're just going to write it as one equation. And since that is so, all of our velocity and acceleration equations become similar. Now, here's the one thing that's a little weird. This is the weird part about 2D. In addition to having two labels, there's one thing I can do in 2 dimensions that I can't do in 1 dimension. And that's this. I can rotate. And now, if you rotate the coordinate system, okay, not only will the numbers be different, but actually your vectors mean different things. I put a prime here, and I put a prime here, and I put a prime here. These are your axes, and they point in different directions. And the thing is that when you talk about the direction of the axes, you're actually making a statement about these unit vectors. So when they say add components of vectors, those vectors have to be along the same unit vectors, constructed from the same unit vectors. Adding components means add up the parts that have the same unit vector. Right now, these guys have different unit vectors, and that is a serious problem. You cannot add these unless you give them the same unit vectors. So how do you do that? Well, let's just say that this angle is theta prime and this angle is theta, right? And so RGA, that's the blue guy, they talk about their angle theta and their unit vector x hat, which points along this direction. That's their x hat. RGB talks about theta prime, which is the angle that they make with their x prime axis, and their unit vector is x hat prime, which points in that weird direction. And you might say, oh my gosh, this seems like it's going to be a real hassle to unpack. Actually, it's really easy. You just take the total angle that it makes, and instead of taking the angle of theta prime, you have theta plus theta prime. And now you're finding the component of this vector that lies along that unit vector. And so now we're back to x hat, y hat. There are ways to transform the unit vectors from one to another, but that's actually honestly much more firepower than you need for something like this. You just say that this is a vector and you want the component of this vector that lies along the x direction. Simply take the whole angle instead of just the angle with the x prime axis. Okay, let's put all of this to work and let's do a problem. This problem looks really hard, but it's kind of like graduation for this video. If you've understood this video, you'll see the steps we take, and you're going to see how short work we make of this thing. All right, I've got a drone, and it's headed toward the ground at 25 meters per second at some angle below the horizon. Presumably that means on Earth. It shoots a ballistic projectile, so that means only under the influence of gravity, and it gives some speed to that. Now, here's the weird thing. It says, relative to itself at an angle of 20 degrees below its trajectory, which is definitely not the horizontal. It says, as soon as it releases the projectile, the drone starts accelerating at some angle above the horizon. If the drone releases the projectile 200 meters above the ground, find the horizontal distance the projectile travels before it hits the Earth and the distance between the drone and the projectile. I will tell you, if I didn't know anything about relative motion, I would probably quit physics rather than do this problem. Actually, I wouldn't. I would find some. Listen, let me say, you don't need to do the problem with relative motion. I just think relative motion makes problems like this a lot more interesting. And this concept of relative motion ends up being really important down the road when you do collisions involving all kinds of particles and stuff, and you want to conserve momentum. They're often best done in what's called the center of mass frame. Anywho, let's collect all the information we have from this problem. In this problem, we are given the velocity of the drone relative to the Earth. And notice I put a negative 30 degrees and a negative 30 degrees here because it is below the horizon. Then they give us the projectile relative to the drone. And notice I went ahead and I already added up those two angles. We said it was 20 degrees below the trajectory. So that's like saying this angle is negative 20 degrees. And we already know that we have to change to different unit vectors in order to add these things. So I just went ahead and I plunked that in right from the get-go. We also know that the initial position of the drone is the same as the initial position of the package, 200 meters above the Earth. And we know that the acceleration of the drone relative to the Earth is this. And finally, the acceleration of the projectile is just minus g because the problem says it is ballistic. Okay? So all we got to do is pick a frame. And the first thing that the problem says is, how far does the projectile travel before it hits the Earth? So this is a collision between the Earth and the projectile. So that's the frame I'm going to use. So in this frame, we say the final position of the projectile relative to the Earth is the initial position of the projectile plus the initial velocity times t plus 1/2 at squared. So all we got to do is make sure we have all of these things. So the initial position of the projectile relative to the Earth, got it, no problem. The initial velocity of the projectile relative to the Earth, that we don't have yet. And the acceleration of the projectile relative to the Earth, we have. So there's really only one thing that needs to be worked out, and that's the velocity. And that's fine. We just use our velocity addition rule. So I have VPE is what I want. So I put a P first and an E last, and I sandwich D in the middle. Why do I sandwich D in the middle? Because one of the things I'm given in the problem is the velocity of the projectile relative to the drone. And so that is something that I have a number for. And so I went ahead, I added these two things together. I did all the arithmetic. You can take my word for it or pause the video and work it out yourself. Make sure I didn't make any mistakes. Okay, what we're left with is something that looks like this. We're actually done with all the physics. This may look like one equation, but remember there's two components, so it's actually two equations. One of them has one unknown and one of them has two unknowns. So this is just a simple quadratic. We solve it for t. Once we get t from this part, we plug it back in here and we end up with these numbers. So this is the distance the projectile goes before it hits the ground. Okay, how about the other part? Now we want to find the distance between Now we want to find the distance between the drone and the projectile, So now what we want to do is we want to be in the frame of the projectile and the drone. So the position of the projectile relative to the drone is the initial position plus v initial t plus 1/2 at squared. So the good news is this we know, this needs to be worked out, and we already know how to work it out. So we take the acceleration of the projectile relative to the Earth, so we want PD. So I start with P and I end with D and I sandwich E in between the two. And all of these things are things that are given in my problem. APE is given, ADE is given, and notice I want AED, so you're going to see a minus sign appear there. So here are my minus sign from AED, here are my minus sign. And so now what I have is a whole bunch of vectors, but notice there's nothing but numbers there. Nothing but numbers. I just say I want this at the time when the projectile crashes, and I already know that time from the previous part of the problem. If you go and you punch in all the numbers, you'll end up with something like this. And this is interesting. Notice that both numbers are negative. What does that mean? That means that even though the projectile started out faster than the drone has been accelerating this whole time, and eventually the drone has a faster speed than the projectile, and the drone actually overtakes the projectile. So the projectile lands behind where the drone is. And moreover, notice that the position of the projectile is underneath the drone, as we would expect, and it's farther beneath it's less than 200 meters beneath the drone. Now, why is that? It's less than 200 meters beneath the drone because remember, the drone is originally headed downward and the projectile continues that path, but the drone starts accelerating out of that path, and perhaps by the time the projectile hits the ground, the drone still hasn't made it all the way back up to where it started. So that's why I say they're just numbers, but they're kind of interesting numbers. And as to the question that the problem asked in the first place, the distance between the projectile and drone, that's nothing but the magnitude of this number. Okay, so that's it. That's all there is to relative motion. If you can get good at manipulating these indices, you can do problems as complicated as this or more complicated. And not only that, this conceptually serves to be useful for lots of other things down the road. Okay, hopefully this video was more helpful than confusing.